Chapter 8 is rational functions. Big ideas here are functions and equivalence. Essential questions: what kinds of asymptotes are possible for a rational function? And are a rational function and its simplified form equivalent? So with this, there were also a couple that had to do with inverses. We're not doing that part of the chapter. We're just doing the rational expressions. So just 8.4, 8.5, and 8.6. Section 8.4 is rational expressions. I can simplify rational expressions, and I can multiply and divide rational expressions. Big ideas here are: much of what's true about multiplying and dividing fractions can be used to multiply and divide rational expressions. I can feel that some of you are going to be panicking right now as soon as I said fractions. Don't panic. It's going to be okay. We're going to just use the same ideas here. So in order to add or subtract, we need the same base. We multiply straight across. We divide by taking the reciprocal. And we'll get to all that as we go through this chapter. A rational expression is in simplest form when its numerator and denominator are polynomials that have no common divisors. We've divided out everything common. A rational function may have 0 or 1 horizontal or oblique asymptote and 0 or more vertical asymptotes. Functions such as f of x equals x plus a over x squared minus a squared and g of x equals 1 over x minus a, as long as x is not plus or minus a, are equivalent. What that means is they're just simplified versions. G is a simplified version of f of x. A rational expression is the quotient of two polynomials. We can think of rational expressions as fractions, ratios, or quotients. A rational expression again is in simplest form when its numerator and denominator are polynomials that have no common divisors, and they show that on the middle of page 527. So they have simplest form and not simplest form. In the not simplest form, there's factors that we can divide out. When we simplify rational expressions, it's important to factor both the numerator and the denominator to ensure our final result is actually as simple as we can get it. Sometimes when we just look at them, we can't tell that they're not in simplest form until we have our factors. And from our factors, sometimes there's commons that we can divide out. Keep in mind that the domains of both the initial rational expression and the simplified form must be the same. Many times we won't be able to see all the restrictions in our final answer. So check all the denominators along the way to make sure the denominators never equal 0. So I like to start off at the beginning and write my restrictions on my domain and then just keep adding to it as I go to make sure I don't miss any. Example 1, simplifying a rational expression. We're going to write this rational expression in simplest form and state any restrictions on the variable. In order to do that, we need to factor. So I'm going to start with my numerator. In order to multiply to x squared, I take x times x. In order to multiply to 10 and add to 7, I need 2 and 5. Since I added, my signs are both going to be the same, and since my middle sign is positive, they're both going to be positive. Same idea in my denominator. To multiply to x squared, I take x times x. I need to multiply to 10, subtract to 3, so 5 and 2. Since I subtracted, my signs have to be different. My bigger number always gets a sign in the middle. Now, restrictions on our variable. Right now, x cannot be anything that makes our denominator 0. So x minus 5 is one of my factors, which means if I add 5, x cannot be 5. X plus 2, that factor can't be 0. So subtract 2, and I get x cannot be negative 2. Now we can simplify here. X plus 2 divided by x plus 2 is just 1. So all I have is x plus 5 divided by x minus 5, as long as x is not 5 or negative 2. And again, I talked about how sometimes in our final answer we can't see all of our restrictions, so we need to check as we go. Here, that negative 2 doesn't show up in our final answer, but it did along the way. So we have to exclude that as well. One other thing I want to note here, guys, is we never, ever, ever simplify by dividing out things that are added together. We only do it by multiplying. And that's because I could have rewritten this as x plus 2 over x plus 2 times x plus 5 over x minus 5. When we multiply, okay, we multiply top, multiply the bottom. It's only when they're multiplied that they cancel, because this factor is the same thing. If we plugged in 5, we'd have 7 divided by 7 is 1. It doesn't work the same way when we're adding. We can't do that here, even though these are both x squared. We can't simplify those because other things are added on to them. It only works with multiplication and division. So, have to be in factored form. Everything has to be multiplied together before we can cancel it out. Now, what is a rational expression in simplest form? State any restrictions on the variables. So, right now, I have this about as simple as I can get it. I have nothing I need to factor down any further. So when I look at my restrictions on my domain, x cannot be 0 and y cannot be 0. Okay, in our denominator, that's where we look for our restrictions. In my variables, I don't have anything added to them or subtracted to them, so the only way that my denominator would be 0 is if I plugged in a 0 for x or a 0 for y. And those are my restrictions. I cannot have those. So right now, I have 3 different things. I have my number parts, I have my x's, and I have my y's. I can take 24 divided by -6 and get -4. When I divide powers with the same base, my base is x here, I subtract exponents, 3 minus 2. Same thing with my y's. I take 2 minus 3. Dividing powers, same base, subtract exponents, and I have this up on the wall, 2 to the right of the happy face parabola. Subtract those and we get x to the first power, y to the negative first power. And we never want to leave a negative exponent. So we're going to have -4x. And only the thing with the negative exponent do we move. We move negative exponents to the denominator or to the opposite part of the fraction and make them positive. So my final answer is -4x divided by y, as long as x is not equal to 0 and y is not equal to 0. And I know that in our final answer, it doesn't matter about the x's, it looks like, but in our original problem, we couldn't have x equal to 0, so we still can't have x equal to 0. Here, because we have things that are added together, we can't cancel until they're factors, things that are multiplied. So, we factor our numerator. Things that multiply to x squared are x and x. Things that multiply to 8 and subtract to 2 are 2 and 4. And my bigger number, 4, always gets a sign in the middle, plus, minus 2. You can FOIL it real quick to check x squared minus 2x plus 4x minus 8, which gives me x squared plus 2x minus 8. And that step you can do even in your head really fast. So, multiply to 6, add to 5 are going to be 2 and 3. And since I added, they're both going to be the same, both going to be negative. Now that I have just factors, I can figure out what my restrictions on my variable are going to be. X cannot equal x minus 2 factor if I add 2, and x minus 3 factor, add 3. So x cannot equal 2 or 3. first of all. That's the restriction on my domain. Now, x minus 2 divided by x minus 2 is just 1. So all I have is x plus 4 over x minus 3. That's my simplified form and my restrictions on my domain. See here, we're going to do the same thing. Our first step when we factor is to always factor out what's common. I'm also going to rewrite this here so that my x term is first. Negative 4x plus 12. It's just helpful to be able to see what we need to factor out. So in my numerator, I always want my x when I'm trying to find factors to be positive. So what I'm going to do is I'm going to take both of those and I'm going to divide by negative 4. I'm going to factor out the negative 4. I'm going to be left with x minus 3. And again, we could FOIL that back and check it. Negative 4x plus 12. So we're good. In my denominator, I have a difference of squares. I need to multiply to 9, subtract to 0. X minus 3, x plus 3. It's called the difference of squares. So restrictions on my variable. X squared minus 9 cannot equal 0, so x squared cannot equal 9. When we take the square root, we get plus or minus 3. We could have found the same values using our simplified denominator. We could have taken x minus 3 equals 0, x plus 3 equals 0. Added 3, subtracted 3. So either way, we get 3 and negative 3 are our restrictions. Now, we can simplify here because x minus 3 divided by x minus 3 is just 1. That leaves me a final answer of negative 4 over x plus 3, as long as x is not plus or minus 3. And again, we can see the minus 3, we can't see the plus 3 because that canceled out, but we still need to list it as a restriction. I'm going to stop this one here.